welcome.
Hello.
Hey there, welcome back. How are you doing today?
Good. How about you?
Doing super awesome. Thank you so much for asking. Welcome back. Glad you can make it. So I guess before I ask if you have any questions, I wanted to see if you can just do this warm-up problem for us.
Yeah. 1 second. Let me get paper.
Sounds good. And just as you know, I'm recording this just like I record all the classes. And I think like we've been doing before, I think I'm going to pause the video while you're working on it. Just
Okay.
not like big spaces where we're not doing anything. So I'll pause right now and then I'll resume when we have our solution. I realized that I forgot something real quick. I forgot something really important. I meant to add the exponents. This is supposed to be 3x cubed. No, 3x to the fourth actually. And then a 4x cubed. And then a 12x squared. Yep. I'm glad I noticed that because that would have not worked out very well if I didn't have that. All right, carry on. All right. So it looks like we have two intervals where it is increasing, right? We should have three intervals where it's decreasing, though. So you have x is less than -1. You have 0, which is less than x, which is less than 2. So that part is good. We're missing one more interval where the function is decreasing. So the way I like to do it is I like to identify all the critical values. So what did you get for your derivative?
I got 12x cubed minus 12x squared minus 24x.
All right. Cubed squared. And then we want to set it equal to 0. So we can tell that because we have x appearing in all three of our terms, 0 is automatically going to be a critical value. So I like to make a list of critical values to help me understand the problem a little bit better. Oh, and by the way, I just want to make sure you're still good with doing a 2-hour lesson today, doing 1:30 to 3:30.
Yeah.
Perfect.
That's good.
Just wanted to make sure. Cool. So our critical values, so far we only have one. We have x is 0. So let's see if we can find any others. I want to start by taking the derivative. I'm going to divide all of our terms by 12x. And we get x squared minus x minus 2 equals 0. Now, something like this is easily factorable. We're going to get x minus 2 plus 1 is equal to 0. X minus 2 times x plus 1 is 0. So the x values that solve this equation are additional critical values. So we have a critical value when x is 2 and when x is -1. So I'm going to fill those in. Perfect. So now what I like to do is I like to make my little sign chart. The sign chart just tells me the sign of the derivative at a particular value of x. So our critical values we have are -1, 0, and 2. So you've already identified that x is decreasing, that the derivative is decreasing when x is negative, well, less than -1, I should say. So you have that part right. And then you also tell me that our function is decreasing on the interval 0 between x is between 0 and 2, which is correct. And then you tell us that our function is increasing when x is greater than 2, which is also correct. So that just leaves one interval left. So the real good thing about having a list of critical values is because it tells us if we're missing anything. Because without critical values, we wouldn't even know if this part we even need. You might just be tempted to think that this is just one interval and it's all decreasing, right? Having the list of critical values just makes it easier to confirm that we actually have all the intervals we need. So I made this, I made a list of the critical values. I made a sign chart, and that's overall what told me that we're missing something right here. So it's always a really good idea to be in the habit of listing the critical points. That way you don't miss anything.
This one for that?
Exactly. So Oh, I didn't see that one. So -1 is less than x is less than 0.
I got confused though. So at this part right here, um, when you said that, we see x in every term, so it's clear that x is also going to equal 0, where a critical value will be when x is equal to 0.
Mhm.
I didn't really think about that. I just went straight to the next step, which was, I divided and simplified and whatnot. And I got x squared minus x minus 2. So the only like critical values I really gave myself were 2 and then -1. And then I started solving for like the signage to the left and right of those 2 points. And that's how I got the 0, comma -5 point. But yeah, I gotta be careful for that.
Yep. All right. So that concludes our warm up. So, how do you feel about this kind of problem? Do you feel kind of comfortable about this, or do you want to do more practice?
No, this is good. But I mean, I remember doing this with the second derivative. I just don't remember exactly how. Like when it's positive, it's concave up. So that tells you that it's increasing. I think you could have done it that way too. I mean, I could have done it that way too. I think that's how it works.
Yep, that situation occurs only when we have a constant value for the second derivative. If the second derivative is positive, that means that the function is concave up on the entire interval, which means we have an absolute minimum. On the other hand, if the second derivative is negative for all values of x, if it's a constant negative number, it means that we have not only a local maximum but a global maximum.
Mhm.
So I want to know if you could identify for me the difference between a local maximum, I guess local extrema and global extrema, or I guess absolute would be the correct terminology for that.
Um, yeah. Could I draw it out or?
Please do. I'm going to put the axes there to help you first.
Okay.
Go for it.
I'm gonna try and think of the actual definition, the mathematical one, at the same time.
Show us some of those art skills we know you have.
Well, if we have a function that goes like this, I'll sketch out our points. We'd have critical values around here and here, right? But actually, is this a good drawing? I'm not too sure that this is a good drawing.
Better than anything I could do, trust me.
I mean, maybe not really, because your art is good, but I mean, like for this exam, for like trying to define the difference or to designate the difference, I don't think this is a good one. Um,
I think it's good.
Local extrema are like they're like the extreme points of the graph. In this case, in this graph right here, we would have a local maximum right here.
Why is that one local, not global?
Um, and the reason why is because our function continues to decrease and increase indefinitely on over here and over here. So this one's a local maximum because it's it's the biggest, or no, it has the greatest y value that's defined, whereas the function just continues to increase indefinitely over here. So um
Yeah, good explanation. So, in a calculus context, how do we use calculus to determine if this point really is a local maximum?
um
I
I
want
would
to add something to your picture that might help us answer this question. So, what did I just draw?
the tangent line.
Exactly. So, what's special about this particular tangent line that I drew?
This one has a slope of 0 because it's horizontal.
And what does that mean about the function itself?
That the function is differentiable.
Well, we know it's differentiable at all points, but there's something really special about the function at this point and also really special about the function at this point right here. So clearly we can see they both have a zero derivative. Where did it go? It disappeared on me. So we can tell that we have a zero derivative at both of those points, which means that it's either going to have to be a local maximum or a global maximum for this one, because we know every time we increase and then we have a zero derivative and then we decrease again, it's going to have to be some kind of maximum. So what if we didn't have a graph to look at? What if we only had some function and the derivative of the function? We would look for the places where we have a horizontal tangent line, and then we would use a sign chart, because if it's increasing and then zero and then decreasing, we know we have a maximum. Likewise, if we have it over here and we have information that tells us the function is decreasing and then it has a zero derivative and then it's increasing, we know that's going to have to be some kind of a minimum, either a global or a local. So my question to you is, how do we use our calculus tools to determine if this is a maximum, a global maximum, or just a local maximum? I guess we might want to use an actual function to help us with that. I like cubics. Cubics are really good at illustrating this point. So I'm going to come up with a quick function real quick. Give me a minute or so. I'm trying to find one that doesn't have nasty values. I'm trying to find one that has nice whole number coefficients or nice whole number values. And I haven't had much luck so far.
Maybe we could try without it.
All right. So I guess let's try to do it without the expression itself, without the equation, without the function. So how do you test a value? For example, if we call this point P, how can you tell using calculus, not using a graph, that P is a local maximum or a global maximum? How do you tell the difference by using calculus?
Well, once you determine that you have a critical value at point P, um, using the first derivative, I think you have to use the second derivative and test x for P. And if the derivative comes out positive, that's an absolute maximum. And then if the second derivative comes out positive, then it's a maximum, an absolute maximum. And if it's negative, it will be an absolute minimum.
I think you have them mixed up. So f prime of x, f double prime of x is the second derivative. So if the second derivative is negative, here, if it's less than zero, if it's negative. So real quick, what can you tell me about the concavity of the function in this shaded region? Is it positive concavity, negative concavity, or zero concavity?
I'm gonna say negative
It is
concavity.
negative concavity. So it kind of goes backward. It kind of does the opposite of what we would expect. So whenever we have a local maximum, that would be, no, sorry, whenever it's a global maximum, this would be a negative concavity. So this is where we have the second derivative would be negative. And then this right here is where the second derivative would be positive. So if for it to truly be a global maximum, we have to have a negative second derivative. And likewise, for it to be truly, for this point to truly be a global minimum, we have to have a positive second derivative. So it does the opposite of what we would expect. So for it to be a maximum, this condition has to be true. For it to be a global maximum, that condition has to be true. And for it to be a global minimum, this condition has to be true.
I mean, it makes sense.
But that's not the only way you can do it. I feel like it's the best way, but another way we could possibly do that would be to take a limit and analyze the end behavior. So we have point P. P has a clear x coordinate and a clear y coordinate. So if we take the limit as x approaches infinity of our particular function, and we get a value that's greater than this. So if this limit is greater than P of x, then we know that this really isn't a global maximum because we're going to have a point outward that exceeds the y value of point P. But I like your way better. I just like to expose you guys to, I say you guys, but I meant to say just you. I like to expose my students to different ways of viewing the problem and different methods of problem solving. But I think overall your way is the most effective. Just do the second derivative test.
No, that's interesting. I didn't realize. I mean, I didn't know that. I didn't know that method of using a limit. That's pretty cool.
Whenever you go back and relearn calculus, you always find things you didn't know before. This is my
Yeah.
fourth time teaching this class, and I'm always finding new things, always picking up on new subtle hints that I never saw before, and it's pretty cool. I always enjoy finding out new things that I never knew before. So I feel like you have a pretty good understanding of figuring out critical values, figuring out local extrema and absolute extrema. Do you want to go over this anymore, or do you want to move on to a new topic?
I think I'm good on this.
Alrighty. So have you guys gotten into using calculus to do curve sketching in your class?
Yes, I've done a lot of curve sketching.
Do you want to do some of that, or do you feel mostly comfortable with that?
I think I'm good on it. I mean, you just use literally just what we talked about pretty much, and then draw the graph. Maybe
Alright.
get another point in there too.
Well,
That's how I remember.
just to make sure, I want to give you a function, and I want you to graph it using calculus tools.
Okay.
So we have this function, we have x squared over the square root of quantity x plus 1. So have at it. Go ahead and graph this function for us. And I want you to list all the relevant information you have. It's fine if you write it on your paper, but also please write it on the board. Write all the information you need to produce an accurate graph of the function.
Okay.
So let's go over this one. So we have our function f of x. I like how you started by taking the derivative. It's always a great place to start. So we're going to use the quotient rule for this one. I think that's maybe too big of a pen size. I'm going to use the smaller size. So we have f prime of x. So we're going to use the quotient rule. Like I said, it's going to be the derivative of the top times the bottom to start us off. So we have 2x times the bottom exactly the way it is. And then we're going to subtract the top times the derivative of the bottom. So the top is going to remain the way it is. It's still going to be an x squared. And then we have to take the derivative of the bottom. So every time we take the derivative of the square root function like this, we have to multiply this. It's just going to be the derivative of our inner function, which is x plus 1. So when we take the derivative of x plus 1, we just get 1. So it's going to be 1 over 2 times x plus 1.
Wait a minute. Isn't it shouldn't it be x squared times the derivative of square root of x plus 1 as the first term?
Yep, x squared. We have the top, which is right here, and then the derivative of the bottom is right here.
But yeah, so what I'm saying is what the two things you just boxed up, shouldn't that be the first term when calculating the quotient rule?
No, it's always going to be the derivative of the top times the bottom minus the top times the derivative of the bottom.
Oh. Okay. All right.
Here, let's make sure that we have this in our notes. So whenever we have a rational function, d dx, if we have some function u divided by some function v, the derivative of u over v is going to be the derivative of the top times the bottom. So that would be u prime v, and then minus u v prime. For the product rule, it doesn't matter, but for the quotient rule, it definitely does matter because the quotient rule is
Yeah,
not
having
commutative
negative.
like the product rule is. Oh, sorry. I meant to make that squared and not prime. So copy this down in your notes if you don't already have it, and we'll continue. I'll be right back. Give me a quick second.
Okay.
So
Good. You're good.
we did almost all of this. The only thing left to do would be to take the bottom and square it. So if we square the square root of x plus 1, we just get x plus 1. And do you have this thing in the box copied down?
Yeah.
Perfect. So now what we need to do to find the critical values, set the derivative equal to 0. It looks ugly, it looks nasty, but it actually works out really nicely. We're going to start by multiplying both sides of our derivative by x plus 1 to make sure we don't have this fraction anymore. The only fraction we're going to have after that would be this one right here, and we'll get rid of that one in due time. So I'm going to multiply both sides by x plus 1, which turns into just this. And then from there, we want to add this entire thing right here to both sides. So I'm going to add this to both sides of the equation, which means we're going to move this to the right side and it'll become positive. And I'm really lazy. I'm going to find the laziest possible way to do that.
I knew it was coming.
And then from there, I don't like having fractions, so I'm gonna multiply both sides of the equation by 2 times square root of x plus 1. But I'm gonna move this maybe a little bit closer before I do that. Center it a little bit because I have OCD. I'm gonna multiply the left by 2 root quantity x plus 1. And then I'm gonna multiply the left side by 2 root quantity x plus 1. So this part goes away, that part goes away. We just have x squared on the right side now. On the left side, what we have is 4. And then we have this x, well, actually we have 4x, forgot about the x. 4x. And then if we, what do we get when we multiply square root of x plus 1 times itself?
Just what's inside, so x plus 1.
Wonderful. So we can see that we have a critical value because we have an x appearing in all of our terms. So I want to make a list of critical values over here real quick. I can't spell, save my life. We have our first critical value. I want to see if you can take it from here. See if you can find the other critical value and see if you can find the other critical information you need to create the graph.
Yeah.
So I want to see if you can take it from here and let me know if you have any questions. So whenever we have an extraneous solution like this one right here, so this is extraneous, but like I said, it definitely solves this equation. It definitely makes the derivative equal to 0. But if we plug it into the radical, just like you said, we get a negative under the radical. We can't have that. It's extraneous. So what that means in terms of the graph is that we have a vertical asymptote at that location.
Oh, wow. I didn't know that. Okay.
So that means the only real place where we have a horizontal tangent line would be when x is equal to 0.
Okay.
Well done. You did really, really well, considering what a difficult function this is. Nice job.
It's interesting. In terms of like this question, all you wanted was the graph of it, right? Like I could plot any points I wanted as long as I was able to draw the function.
Yep, that's reasonable.
Okay. Would you like me to list out the points or?
Don't worry about that. This is
Okay.
perfectly okay. So I think we are good on curve sketching. Have you guys done any optimization?
Yes. Optimization though, that's not I learned it in a rush. So if you can go over that, that would be great because that was, man.
It's pretty tough. Everyone has trouble learning optimization when in a first year calc class.
And like it's also kind of dependent on the situation too. So man, that quiz was, I mean, I got it on the quiz, but obviously, once the stress of the quiz was gone, I don't think I remembered it the next day. So
That makes sense.
this should be really, but otherwise it's interesting.
So what is the most recent topic you guys covered in class?
More differentiation rules, and then it was something else, one more thing. And the differentiation rules are the ones that you came out with in the beginning of our class. So, for example, product rule, chain rule, quotient rule, those ones that I learned in the beginning of this one, that was like the most recent one.
It's weird how you guys did all of this calculus stuff and you just learned those differentiation rules before now. It's interesting how they structured your class.
Yeah, I don't know. And we've been, well, actually, no, we haven't really had problems with those yet, but they weren't too bad. And then exponential functions was the start. It was the second assignment, the last one that I did. Obviously I have two more to tomorrow, but um that was the beginning of it started with exponential functions.
Nice. So you're pretty good with exponential functions, having worked with me a little bit. So you're probably far ahead of your classmates.
Probably. They say it's hard, like we talk in a group chat, and a lot of them, they say that, like, I don't know, I think they leave it for the last day. It's kind of like me, but they don't give themselves enough time. And remember when I told you how like there was this one problem where they didn't specify exactly where you should round. So I had to like take the time to like solve it and round in different areas of the problem. I think that they don't really have they don't allow themselves like time to do that stuff. And then, they have to ask for an extension or whatnot, which is probably what makes the class hard. But
Yeah, exactly. When I first took calc in high school, we had, I think, 50 kids in the class initially. And
wow.
people thought they could just kind of breeze through it. Like algebra and pre-calc weren't too bad. I think we had 7 kids drop the class before our first test because it was harder than they realized. They can't procrastinate. Senioritis isn't helping them in learning calculus. So that's why we've had so many kids drop the class.
Yeah, it can be tough. So I've learned to give myself time to finish my assignments and whatnot. And I think I just do them. I'll just do them tonight rather than tomorrow, since tomorrow I'll have more classes than usual too.
See, that's really smart. I wish I was that smart when I first took calc. My life would have turned out maybe differently if I had.
I mean, easier said than done. When it comes down to it, it all depends on what I'm gonna do tonight.
You're right. Gonna party up.
I'm gonna try not to. I told my friends, listen, I got some stuff going on. I got a lot of, this is a busy 2 months ahead of me, and I might not have to, I might not be able to, play or whatever. So we'll just have to see.
All right. Don't forget to just have fun being in high school. I mean, it's so, I can tell that you're kind of a high achiever. So let me give you some advice. Don't have school be your only priority. Set aside some time to have fun and be yourself because you'll never get the time back. You'll never, ever get it back.
Yeah. I
All right.
try,
So optimization. What is optimization exactly? Just in a general sense. What does it mean to
maximizing
optimize?
or minimizing certain values.
Perfect. And how does optimization work from a calculus standpoint?
Um, in terms of calculus, all I know is that I'm pretty sure the first derivative is you're gonna be your best friend, I think.
You are right. Well, the first derivative and I, we're not on the friendliest of terms, but you're right. It is absolutely useful in optimizing quantities. So I feel like like I said, this is my 4th time teaching this class, and in my experience, it's always best to start maybe just with an example to help illustrate what we're really trying to do here. An example really is the best way to teach. So I am going off my textbook right now, the textbook I used to teach this class.
Mhm.
And let's say that a farmer has 2,400 feet of fencing. I think I'm going to bring down the font size a bit.
Yeah, this is interesting. Now, this just came into my mind, but in seventh grade, we in my math class we had a thing where we were trying to make these boxes of cereal, basically, but we wanted to like basically we wanted to maximize the volume and see who could use the least amount of or see whose box in the end had the least amount of surface area. And I asked my teacher that day, I was like, how could you how could you get a greater volume using less surface, I mean less material, it didn't make sense to me. And she said, oh, that's a calculus question. And when I told my parents, they said, oh, she probably just didn't know, but now that I think about it, it actually was a calculus question.
That's interesting. I wish my seventh grade class touched on things like that, but I totally understand what you mean. So we have this box. We can, if we cut bigger corners for the squares, we're going to maximize volume. If we cut smaller corners, we're going to minimize volume. And we need expressions for both the volume and the surface area in order to properly use calculus to minimize what we're trying to minimize or maximize what we're trying to maximize here. And it would just kind of get folded up like that if we fold up the flaps. And we
So
get
that's the
this.
fence that you're erecting right now?
Nope, sorry. I was just drawing what you were describing, but I kind of
Oh,
got off
okay.
focus. Sorry.
No, my bad. I didn't realize. That's, but that makes sense too. Uh, I had some time to think about it. 4
So,
years.
so back to the problem.
Yeah.
We have an amount of fencing that we can use, and our farmer wants to fence off a rectangular field that borders a straight river. So drawing a picture is always really helpful. So here, let me at least try to be a little creative here. This is my super detailed drawing of a river. I hope you appreciate it because I put so much effort into it. And
oh, you drew it?
For lack of a better word, yeah.
I thought you got it off the internet.
Yeah, it's that good, isn't it?
Yeah, it's so detailed.
I know, right? And the idea is that part of this, there's only 3 sides of the fence.
Yeah,
So
yeah.
the river
is a natural border.
I guess he's just kind of banking on the fact that his animals aren't going to go crazy and hop in the river. I don't know if that's wise, but I guess that's what's going on here. So we have an amount of feet of fencing. He's trying to create this fence. He's trying to create fence off the field, and then he needs no fencing along the river, as we can tell by the picture. What are the dimensions of the field that has the largest area?
Also, I think in at least most optimization problems, you'd also want to find the constraint equation, I think.
Exactly.
It doesn't always apply. It tells you I think, oh yeah, it tells you that for example, in this case, our constraint equation would tell us that the amount of fencing that we have to use has to equal 2,400 feet. That would be it.
So,
and then it's just up to us to create variables and maximize or optimize those variables.
You're right. I kind of consider this to be like related rates 2.0. We need equations that accurately model the situation, and we need to use calculus to manipulate those equations to get the result. So let's take a look at what we have. Let's take a look at what we need. So this constraint, can you create an equation that accurately describes the thing that the constraint is telling us?
Yes.
Let's
so
see
I'm going to label the picture.
Mhm.
And I'll just look at this as a rectangle from now on. Our constraint equation would be that, which tells us that, yeah, our fence has to equal that much.
Perfect. And then now we want to find the quantity to be optimized. So what are we trying to optimize?
Area.
Perfect.
And in that case, it's just going to be LW.
Mm-hmm.
It's kind of a fat L, sorry.
No worries. That looks like lowercase gamma upside down. The lowercase gamma kind of looks like that. So we have a constraint.
Excuse me.
We have a thing that we're trying to optimize. So how do we take it from here? What would be the next logical step?
Next logical step would be to find W and L.
Exactly. That is the end goal. Ultimately, that's what we want. But how do we get there, though, is the thing.
How do we get there?
Because L is a very specific number, and W is a very specific number too, that both produce the maximum area.
I would say
Maximum
we should
possible area.
solve for L and then substitute that into maybe both equations or maybe just a constraint.
I think, well,
Actually, I think just a constraint.
Yep, that's a great idea. So take the constraint. We're going to subtract both sides of the equation by 2W, and we get length is 2400 minus 2W.
Yep.
And we'll substitute that in right here for L. So show me what that looks like. I'll start off with A equals and then finish it off for us.
Okay. You want me to expand?
We're going to need to expand it in order to take the derivative most efficiently.
Okay.
Perfect. So we are trying to optimize the area. And whenever we do that, we have to do exactly what we just did. We have to put the quantity to be optimized in terms of just one single variable. And then we want to take the derivative of both sides of the equation. So go ahead and show us what that looks like. Find for us dAdw. All right, wonderful. How do we find critical values?
We set the derivative equal to 0. So I'm gonna, should I do that? No, I'll keep everything the same. Okay.
All right, we have our single critical value. What do we do with this information?
Well, I think that we optimized it just now by taking the derivative and then setting it equal to 0.
Yep, but we want to
So
confirm that this really is the maximum.
this is the max. To do that, I think either that limit thing that you showed me earlier or a second derivative test
Both of those would work, or we could use a sign chart. So if we plug in 0
or
into
a sign chart. Yeah, let's just do that.
So if we plug a 0 into our, we're not going to do the derivative this time. We're going to be plugging it into the area equation. So if we plug in a 0 into our area equation, the whole thing would become 0. So we know that it would be less in this region. If we plug in, for example, 601 into our area equation, we would also be getting smaller. Actually, you know what? I think I like your idea better, doing the second derivative test. So show us what that part looks like.
Okay. Shoot. I don't remember the notation, the double derivative, or no, the second derivative notation when we have it like this. What would that? Would it just be dA
We could just write
or
it
d squared? Oh, it's just d squared. Yeah. Okay.
over dw squared.
Yeah. W has to be. Oh, yeah, that makes sense because we're doing it for W again. So so the second derivative is equal to -4. That's a specific value. -4 means that That it's
It's
concave up.
concave down on that entire interval.
It's concave down?
Yep, because whenever the
Yeah,
second
yeah, yeah,
derivative,
concave. Yeah, okay. But then that means that it's a um that means that it's a maximum, right?
yep, exactly right. Whenever it's
Negative
concave down, we
maximum.
have a maximum. So perfect.
Okay.
So what
So
is,
that means that 600 is the maximum for W, right?
we want to find
Okay.
the maximum for L now.
Well, wouldn't W substituting W into whichever equation we want find theoretically the L quantity that we want?
Well, we can't do it for the area. And the reason for that is because we don't know A. If we knew A, we could do it, but we don't know A. So we're going to have to plug it into the constraint and find W.
Why would we need to know A though? Because if we get W and then we have an equation for L, we know that W is optimized. So whatever comes out of L, shouldn't it? It should. I think that it should be W's optimized counterpart, and then we can solve for A, right? And then we get the answer to the question.
Well, they don't ask for the area. They just ask for the dimensions of the field. So in other words, they want L and they want W. They don't care about A.
Oh, okay, okay.
So W is 600. If we knew what A was, we could just solve for L. The problem is we don't know A, we don't know L. We have an equation with two unknowns. Can't solve that. So we have to use the constraint instead. So I'm going to take 2400.
So we're gonna have to repeat the whole process, huh?
Nope, much easier than that. So I'm going to take 2400 equals 2 times W plus L. I'm going to plug in 600 for W.
Yeah, yeah.
And then we get an L value of 1200. And we're done. We have W and we have L. So if our dimension,
we don't even need A, huh?
we don't need A, they only ask for L and W. They only ask for the dimensions.
Okay, so 1200 feet by 600 feet. Should we
Yep.
check it?
Well, you checked it just now by doing the second derivative test.
Yeah, and 600 plus 600 plus 1200 is 2400. So
Perfect.
okay.
All
So
right.
this was optimized in terms of maximizing it, right? Okay. Are we gonna go over other like minimizing?
Yeah, definitely.
Okay.
Am I good to erase all of this?
Yeah, yeah.
Cool. So the next problem in my book tells us that a cylindrical can is made to hold a liter of oil. We want to find the dimensions that will minimize the cost of the metal to manufacture the can, and I'm going to type all that up right now. So it's always a really good idea to start with a picture. We have a can that holds 1 liter, and we are trying to minimize or maximize the quantity, either one of those two. So what would be a really good place to start now that we have the problem written and now that we have a picture drawn that describes the situation? So remember what we did last time. We want to identify the constraint and we want to identify the quantity to be optimized.
So the constraint I manufactures to hold. So the volume of this cylinder, it has to equal 1 liter. So the volume is going to be 2 pi r squared plus, how do you, I think the surface area of this, excluding the bases, is just the height times the circumference.
Well, it's interesting that you mentioned that. So when I try to find surface area of something like that, I want to imagine I'm cutting the can in a straight line like that. I know it doesn't look like it, pretend like it's perfect. So I'm cutting this. I'm going to pop the top off, pop the bottom off, and then I'm going to unroll this part that
Yeah.
revolves
So
around
actually, yeah, it creates a rectangle.
in
The
two
rectangle,
circles.
and
A
then
rectangle in two circles.
this is the rectangle. Yeah, the rectangle and two circles.
So
This is
this
the height of the whole thing, and then the length is gonna be the
circumference.
circumference. Yeah.
Yes.
So 2 pi. Okay. I'm gonna write down the constraint equation.
Be my guest.
Oh, wait a minute. Why am I even solving? I'm solving for volume. This is gonna be sorry, I had a brain fart. Okay, so the constraint equation states that 1 liter, the volume is equal to the area of the base times height of the prism.
Oh, that's what. We don't really have a prism though. What prism are we talking about?
Well, the height of the cylinder, then I actually should say.
Yeah. Eight. Yeah, H is just fine. We can just leave it as H.
Well, wait, do we have H? We have H though. Oh, no, we don't have H. Sorry.
We
Okay,
don't have H, but we can find it.
we can find it.
Mhm.
Hmm.
So this right here is a constraint, and we're trying to minimize the cost of manufacturing each can. So what does this part of the problem mean in terms of the thing we're trying to optimize? Can you create an equation for our quantity that we want to optimize?
Uh, I would assume that the cost refers to how much material is used for each can.
You're
So
right.
that would have to do with surface area.
Absolutely. So we're going to
Oh,
take the
so
surface area
okay.
equation and optimize that.
Okay, I thought I brought up surface area for nothing, but it turns out we need it. So
We definitely do.
so
We'll just have A be surface area. See if you can create the equation to find surface area of one can.
okay. This is gonna be okay, so that's 2 area of the base plus surface area, or plus lateral surface area. That's what I just solved for.
Mm-hmm. That's correct.
I think it can be no, simplified too.
All right. What do we do from here?
Well, we've identified our equations.
Mm-hmm.
Um, we want to create we want to create the equation that we want to optimize, and we want to put it in terms of one variable.
Right.
So we're going to use the constraint equation, and I would say we could solve for H and then put the actual equation all in terms of R.
This is kind of tricky though, because the constraint is a volume and our quantity is going to be an area. So we might want to convert the liters we have, into something that translates nicely between volume and area. So How about we convert this into cubic
Milliliters
centimeters? I'm
or
thinking,
cubic centimeters? Yeah, same
yeah.
thing, pretty
So
much.
a liter is equal to 1,000 cubic centimeters.
Hmm. That's a good idea.
So now we can use this information to put either R in terms of H or H in terms of R.
I'm gonna use H since R is squared. Will I? Yeah, yeah, and it's simpler that way, at least in the short term. Maybe not in the long term.
Great.
Okay, so that's that. Then we're gonna take the derivative of this equation and then set it equal to 0.
Mhm.
Okay. I So I used the quotient rule for the second term. I think
Mhm.
that's what that came to be.
Yep, and you did that correctly.
Okay. Um, oh, man, that doesn't look good either. Okay. That does not look good.
That is correct, though. You have the right answer.
Wow. Okay.
How do we verify that this really is a dimension that minimizes the surface area? How do we prove that it really does do a minimum for us?
Well, we could use the second derivative test, and if it and if we plug in that for R and we get I think it should be a positive value. Then the graph will be concave up, and that will be an absolute minimum. And that way we'll know that it is fully minimized.
In theory, yes. But the problem with this situation is that when we take the second derivative of this whole thing, we're going to continue to get higher powers of r in the denominator. If we only got a constant, if we only got a single number for the second derivative, we'd be good to go. We'd be finished. But the problem is, if we take the derivative of this, we would get 4 pi plus 2000 over r to the fourth power. And that's why we can't use the second derivative test in this particular situation. We're going to have to find something else. I want you to think about it for a few minutes, see if you can think of another way to prove that this generates a true minimum.
Would it have anything to do with the constraint equation?
Well, we're still going to do something with the derivative.
But I mean, in terms of proving that the value that we got for r is fully optimized, we it wouldn't, we couldn't use the constraint equation, could we?
Not in this situation, no. Good
Okay.
guess, though. What we want to do is we want to take our critical value and make a sign chart, just like we did when we were finding increasing
Oh,
and decreasing function behavior on particular intervals. So our critical value is cubed root of 500 pi. Not a nice number to work with at all.
nope.
So we know that we have a zero derivative there. We want to find the derivative. We want to find the rate of change of the function for x values that are less than this, and then do the same thing for x values which are greater than this as well.
For less, we can use 0, I would say.
You're learning the ways to be lazy. I feel proud of you.
I mean, you can't call yourself a mathematician if you aren't lazy.
That's true. Unfortunately, we can't use 0 because if we look at our derivative, we have,
Oh, dang it.
let's
Maybe
use 1.
1?
Yep, 1 would be great.
Yeah.
So we have
Okay.
4 pi minus 2000. That's absolutely going to be negative.
Yeah, that's for sure.
But then what would be a good value to pick that's greater than this?
I would say can I calculate what that would come to approximately?
You could, but there's maybe another way we could do it as well. Like, what if you didn't have a calculator on the test? May God have mercy on your soul, but you might have something just like that. So in this situation, if I didn't have a calculator, I'd probably round pi up because we're trying to find a value that's much bigger than this. So I'd round pi up to 4. I'd make
It's cube root of
20,000.
1500.
It would be,
Or no, 1005.
it would be 2000 because if I round pi up to be 4, we would have 4 times 5.
Oh, you're rounding to 4.
Yeah.
Why 4? I would have rounded it to 3. Are you rounding to 4 because you want to maximize this so that we can approximate something that's definitely larger?
It's because I'm looking for something that I know with absolute certainty is greater than this. And if we round pi up to 4, it absolutely will be greater. So I'm just trying to pick
True.
something I know will be greater than this value. With 3,
Okay.
it's kind of uncertain, but if we pick 4, we know for sure it'll be bigger.
Mm.
And then cube root of this thing right here. So I might want to approximate this. I might want to make this 2, 4, 3. And the reason why I want to do that is because, if I'm not mistaken, the cube root of 243 is 7. So we would have then cube root of 10 left over. So this would be 7. And if cube root of 10, no, sorry, if cube root of 8 is 2, and cube root of, shoot, what else is there? And then cube root of 27 is 3, this would be somewhere between 2 and 3.
So you could just put down 3, maybe.
Yeah, we could.
Wow, this is where calculus is. This is probably what my peers are saying is hard.
This is where things get mind-blowing. And just wait till you get to vector calculus. Things get much more interesting even then. So this would, yeah, you're right, 3 would be our upper bound. So we could pick anything. Let's pick 21. Or actually, you know what? I would probably maybe just do 30 just to be absolutely sure we're picking something that's bigger than this right here.
Okay. So 30.
So find what the derivative is when r is equal to 30. And we have about 5 minutes left. I think after we finish this problem, we're just going to call it a day, because
Okay.
my algebra class starts immediately after this. It starts promptly at 3:30.
Okay, okay.
You know, I think I'm going to make some videos about vector calculus. I think I'm going to like make a full video series about it, because I always thought it would be interesting, and there aren't too many videos about it.
Okay, I'll definitely be watching. Not sure how much I might I mean, I've done vectors before in physics, but I don't know if it's the same as what you might go over.
We deal with slope fields mostly. Are you familiar with vector fields at all?
Uh, no, I don't think I am.
We deal with things called partial derivatives, which look like this, where f could be a function of multiple variables. Typically, it's a z that depends on x and y. So it's the derivative of a multivariable function with respect to something. Maybe just typically time would be the parameter in a situation like this. So this would be a partial derivative. And we know a normal derivative gets us a rate of change, right? A partial derivative tells us not the slope of a tangent line, but the slope of a tangent plane. So if we have some 3D function that looks kind of like this,
Wow.
a tangent plane at a particular point would be like this, and the partial derivative tells us the different gradient vector components of
Oh my
this
gosh.
tangent plane. Really cool stuff.
That looks crazy.
I liked it. And you also learn how to do multiple integrals, which give you not areas, but they actually give you volumes. I don't want to spoil the surprise. You'll get there soon. That's what you have to look forward to.
Okay. Well, that's yeah, that is a little mind blowing.
It really is.
Tangent planes.
Tangent plane.
I knew you could have them, but I didn't know that, you would ever need to calculate the derivative of them.
Well, if you study science or engineering, or yeah, I think maybe mainly just those two fields, you're going to want to know how to do it.
Yeah, yeah.
So let's take a look at your results. So we have a negative derivative, and then a zero derivative, and then a positive derivative. So what does that tell us in terms of the quantity to be optimized, considering that this is the derivative of that quantity?
That this is a low absolute minimum, and that it's concave up. So R in this case would be fully optimized or minimized in this specific case.
Damn, we've proved it. Well, you did. You did most of the heavy lifting, so nice work.
Not without your help, but so
I'm blushing.
Find the dimension. So we have R, and then all we would need is H.
Yep. And we have a formula that will give us that right away. And because we use this equation right here and not the top one to find the derivative, we want to use this one again to find H.
I mean, isn't that H right below it?
Well, Yeah, you're right. We want to just, yeah, you're right. It makes more sense just to use that one at the bottom.
I mean, that's what it is. That's the constraint equation, but solved for h.
Yep. But we don't really need to do that. This is just tedious algebra work, plugging in r and finding h.
Yeah, that
I'm
would
not going to
be
waste our time doing that, but I do want to assign a homework problem for you to do real quick. Another
okay.
optimization problem.
Okay.
So let's say we have the function f of x equals e to the x plus 1. And I want you to find a point. Here, I'll type it up. I think I'll just generalize and call the point P. And I meant to write along, not alone. I can't spell clearly.
I figured, yeah.
Point P along the line x is -1, but minimize the distance between point P and our function f of x. So it doesn't look like it, but it is also an optimization problem. We're going to have a constraint, and we're going to have a quantity to be optimized, and we're going to have to use the first derivative to help us.
Okay.
So I recommend you take a snapshot or write it down real quick, and then as soon as you have that, you're free to go. I think I've tortured you enough today.
I just have one question.
Sure.
Is chain rule going to be involved in taking the derivative of the original function at all, or no?
Well, remember what we talked about in our last class? We automatically do the chain rule for everything, but the thing is that when we take the derivative of the argument of this function, what do we get?
Yes, yes. It just becomes itself, so.
Yep, you're right.
Okay, so then I shouldn't have to worry about it too much?
Nope.
Alrighty, well, that sounds good. I'll have it done. Thank you. And is this the last makeup, or is there one more if
I think there's one more. So I think on Thursday we'll do another 2-hour session if that works for you.
Yeah, that'd be fine. That'd be great.
All right, perfect. Well, as soon as you have this copied, you're free to go. Have a wonderful day, and I'll see you Thursday.
All right, thank you. You too. Good luck with the rest of your day and the rest of your classes.
Thanks so much. See you next.
Bye-bye.